Good evening, everyone. So this is Kavana S. from Sri Venkateshwara College of Engineering, Department of Information Science and Engineering. Today, I'm going to say about the fall risk prediction using wireless sensor insoles with machine learning under the guidance of Chetan C., Assistant Professor, Department of ISC. So now let us see the contents. So the contents are introduction, related background, working or implementation, future enhancement, conclusion, and the references. Now let us see the introduction part. So the accidental fall is a significant health risk among the elderly. However, most of the fall detection system give notification only after a fall occurs. Therefore, medical attention has shifted to fall preventive measure to reduce risk of fall and prevent any damage entirely. Medical research shows that the aging process in human involves the recession of nervous system and psychological function, which reduces their ability to work. Most were post-fall detection system, which notifies the caretakers or the medical staff only after a fall occurs. However, despite the early notification, damage has already been occurred. Therefore, there is a need for a fall prediction system to prevent falls from occurring at an early stage and help the elderly to reduce their fall risk. Therefore, a fall risk prediction system which can notify the elderly before the fall using previous data is in a promising method to avoid falls. Although there are many studies based on fall risk prediction system, most studies used accelerometer sensor data or a static pressure plates. A wireless sensor embedded smart insole for fall risk prediction has been proposed. So the smart insoles are used to enable dynamic gait analysis. Here, gait analysis, it's nothing but it's the analysis of an abnormal activities or abnormal condition of an human. So since the gait and the balance disorders have been identified as a strong fall risk factors, we used features such extracted from the gait and balance data for the study. Then apply different ML models, that is machine learning models, and compare their performances on fall risk prediction. In addition, the smart insoles are lightweight, thin, and comfortable to wear, providing an unobtrusive way to perform gait and balance analysis. The below is a simple diagram to understand. So the next is that the related background. So here is an author called Reem Broom, Jade Nasreddin, Frederick Bernadotte, Mohammed L. Pedrayo, Mohammed O. Dio. So they've proposed this, a fall risk assessment using pressure insole sensors and convolution neural network. So the work says that this is an alternative method of representing signal as heat map images and using CNN, that is convoluted neural network, with the optimization method to predict the risk of falling in 411 subjects over the age of 65. So the next author comes from Chanason Nutaswapon, Sakchai Chaumakor, Vivet Ungakau, Noprait Chintayas, then Somachok R. So they propose this human fall prediction and detection using low price IMU sensor. So they designed the device using the low price MPU 6050 sensor to measure the body acceleration. This device will be attached to the body, that is hip, for collecting the acceleration data. So next is Jayashri G, Padmavati S, and Shantini. So they proposed an explainable deep learning model for vision-based human fall detection system. And they says that ensure fall detection through deep learning classification using a convolution neural network with hidden layers. Okay, so the next comes as the working. So the working, the step one. So the step one says it's a general information. They collect the general information. So there a total 1,101 volunteers participated in this study. So excluded participants were subject with a plantar wound aged below 65 years, an unstable medical condition, gait, and inability to walk 10 meters without support to wear smart insoles. So a fall risk assessment index called timed up and go data were also collected. So the timed up and go, which is also called TUG, is a simple screening test that is sensitive and specific measure of the probability of falls among older adults. One of the primarily used tests for fall risk assessment by experts. The below is a diagram where for this diagram, the TUG has been conducted. So here the number 1 stands for stand up, the number 2 is for walk 3 meters, and the 3 is the turnaround, and 4 is walk 3 meter, then 5 is a sit down. This is the general, general information. So the next is step 2. So step 2 is a smart insole, which is also called as Surosole. So here, a commercial smart insole was used to collect dynamic plantar pressures while a subject was walking. So the diagram here represents the foot zones position. The data collected during the experiment were divided into 5 zones of the foot. So the 5 zones is that the big toe, HA, which is called as the big toe, that is hallux. Then the M1 is called as the medial forefoot, and the M5 is the lateral forefoot, and the MF is the midfoot, HF is the heel. So these sensors were connected to the microcontroller using a voltage divider circuit. So then the output was then connected to a 10-bit analog to digital converter. So the circuit was adjusted for each sensor to operate a full force range, like approximately 0 to 20 kg, and a response time of less than 10 µs. The sampling rate was 20 hertz. So the dynamic data collection process began with the patient walking back and forth over a 10-meter distance to assess the pressure distribution under their feet. So this real-time measurement was transmitted to a smartphone through the Bluetooth, then recorded on a database server for further analysis. So here there is a diagram of another called the smart insole layer and the location of a sensing point. So there are 3 layers, that is top, the sensor layer, and the bottom layer. Okay. So next is the step 3, that is the pre-processing step. So after the collection of data, the sensor data at the beginning and at the closing of each sample was cut by 20%. So this percentage of cut was selected based on the evaluating different cutoff percentage on the collected smart insole data to eliminate the transition of the start and the end of the data collection. Okay, so to enhance the feature of the fall prediction and gait analysis, a collection of COP from 2-step walk cycle called the butterfly loop was introduced. So the below shown figure is nothing but it's a butterfly loop that traces the COP. So now we can coordinate the butterfly loop in the figure as shown. It is defined as A, B, C, D, E, F, G, H, I. So where B is a cross-section point of the butterfly loop. So the common extracted feature of gait analysis obtained from butterfly loop are shown here. The first one is cadence. So cadence is nothing but the number of steps a person walked in 1 minute. Then comes the stance time. So the stance time is nothing but the time taken to complete a stance phase of corresponding foot in gait cycle. Then comes the sway distance. So the sway distance is nothing but the distance obtained from the corresponding segment of the butterfly loop. The larger the sway distance, the larger the pressure applied on the foot. So here the DL says that the left sway distance, that is equal to BE plus EA plus AD plus DB. So that's what this. The last is that the cycle time. So that is the time taken to complete a gait cycle, that is the 2 steps. In other words, the time taken to complete a butterfly loop. So the below graph says the features and their corresponding scores. So it is a what to note that this butterfly features have been used for gait analysis, but to the best of our knowledge, it has not yet been used for fall risk prediction. The additional feature extracted from the butterfly loop for fall risk prediction are presented. Okay. So the next is the step 4. So step 4 is the feature selection. So the selection of features is a central concept in ML, that is machine learning, that has a significant effect on the model's performance. Irrelevant features may adversely affect the performance of the model. Therefore, good selection of features will result in reduction of overfitting, improve accuracy, and reduction of training time. We use a method called feature importance to extract useful feature in our data set. In this, all features have their individual scores. Features having a high score are more important for the target outcomes, that is, the high risk of fall or low or no risk of fall classification. So here, the techniques or the ML we have mentioned is that we have used neighbors, decision tree, k-nearest neighbor, and the logistic regression and the random forest, and also the last is that SVM, that is support vector vision. So in this, we have used a 6 well-known machine learning models. So the next is the future enhancement. So how this can be implemented in further notice. So the first is that the high accuracy performance can be achieved by using deep learning methods. We will explore different deep learning methods to extract insights of human balance with the help of hidden layers of neural networks. In addition to that, it can be investigated with more gate and balance features from Insole data to develop a multiple class fall risk prediction model. Then we can use a data set containing a real world gate and unsupervised patients continuously recorded with foot own initial sensors over a period of 2 weeks. So the next is the conclusion. So in this, as we said, 6 different ML approaches are compared to predict the risk of falls by using the butterfly loop gate or the balance assessment obtained from wireless pressure embedded smart insoles data. So this was evaluated on dataset of 1,101 elderly subjects walking data collected using a pressure embedded smart insole. So that is the logistic regression model with oversampling achieved the highest AUC, area under the curve of 0.82, that is the highest, and the RF model with oversampling achieved the highest accuracy of 0.81 and specificity of 0.88. So therefore, the results suggest that have the potential to predict the risk of falls using wireless pressure sensor embedded smart insoles. The next comes the references. So these are the references. Thank you.